this example 3 will be about the application of the charge moving as a circular path by the magnetic field. So it is the principle of the mass spectrometer. So mass spectrometer is actually a instrument to separate the different isotopes of nuclei by the radius. Okay, and here we are going to see how. Okay, so in our situation, the two isotopes of helium nuclei, helium-3 and helium-4, are accelerated through the same potential difference. They enter the region of uniform magnetic field. So this is region of uniform magnetic field at S2, so coming in this way, and follow the semicircular paths with different radii. So they ask you to determine the ratio of the radius of helium-3 to that of helium-4. Okay, so now let's see the properties of the helium-3 and helium-4 first. Okay, so we start with helium-3. So helium-3 consists of 2 protons and 1 neutron. Okay, so when it consists of 2 protons, that means the total charge of helium-3 is 2e. Okay, but when we consider the mass also, we need to also consider the mass of neutrons. So the mass of helium-3 is considered as 3u, or 3 times the mass of protons. Okay, and for helium-4, helium-4 consists of 2 protons and 2 neutrons. So that the mass of helium-4 will be 4, and the charge will be the number of protons, which is 2e. Okay, so then we bring both helium-3 and helium-4 to be accelerated through the same potential. Okay, so with the acceleration, we use the principle of energy conservation. Okay, so that the potential energy that we use to accelerate the nuclei will be equal to the kinetic energy. Okay, so that will give you the QV for the potential energy, and it will give you the K as for the kinetic energy. Okay, so for helium-3 and helium-4, we are given that Q1 equals to Q2. So when Q1 equals to Q2, K1 will also equals to K2. So that they have both the same charge and kinetic energy. Okay, so just note that they have the same charge and kinetic energy. And then we are going to consider the circular motion. Okay, so we have proof from the first examples that for the circular motion under a magnetic field, and the radius can be found by mv over qb. Okay, so then if we try to rewrite these equations in terms of k, okay, so I'll just put square on both sides of the equation so that I have r squared equals m squared v squared over q squared and b squared. Okay, and then if I want to write this down in terms of k, or half mv squared, I separate half mv squared to here. Then we have another m here from m squared v squared, and then when we put the half or 1 over 2 here, we need to times this expression by 2. Okay, So that's we have 2m, and the rest of the equation we have q squared and b squared. So that's we have r squared equals to k, or kinetic energy, and times by 2m, so it's 2mk over q squared and b squared. So from this equation, okay, so as we have the constant magnetic field, so B is constant, and also we have also shown that Q or charge of helium-3 and helium-4 are the same, and also the kinetic energies are the same. So K1 equals K2. Okay, so that's the variables in this equation. We have that K is the same, B is the same, Q is the same. So it would be R squared is proportional to M. Okay, or you can also say that R, or the radius, is proportional to the square root of mass. Okay, so in this term, if I put R1 over R2 on the left hand side of the equation, on the right hand side of the equation would be the square root of M1 over M2. Okay, and the R1 is actually the radius of helium-3, and the R2 is actually the radius of helium-4, and the mass of helium-3 is 3u, and the mass of helium-4 is 4u. So we cancel the u, or the proton mass here. So we have the ratio between the radius of helium-3 and helium-4 to be square root 3 over the square root 4. And that is our answer.